Another draft physics video presentation. DraftScience on YouTube. Anyway, TinManPower. This will basically be a response video to a couple of videos he made, and we'll see if there's any conversation possible. I'll post the link anyway. We'll see what happens. And then I'll do some comments at the end. So we'll just get to the Tin Man basic stuff quickly as possible to spare him any unnecessary extras. So he made two videos, Induction Myth, which, I think he's got that backwards. He's the one with the mythology. And then Magnetic Gate, he called it, but he's really arguing for some sort of non-conservative field, and as soon as somebody says non-conservative field, they're implying some sort of extra energy source or some way to break the rules where every action has an equal and opposite reaction, or the rule that you can't create energy and you can't destroy energy, that any imbalance you create in a system, the imbalance has a left and a right. You just can't, if you're creating more up, there's more down somewhere. If you're creating more right, there's more left somewhere. It's just the way it works. That's physics. So I guess I'll do that one first, just because it's kind of a simple principle. So you can sort of see in this thing has a pendulum, and the idea is a magnet down here and a piece of metal here, a rather heavy piece of metal. And he's kind of arguing that the angle at which it sticks to the magnet is different than the angle at which it releases from the magnet, and therefore that's non-conservational, blah 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 blah. So the simple answer to this is that he's not accounting for the fact that the angle matters to gravity. So in a sense, you have to fight gravity to stick to the magnet in the first place. You have to go up against gravity, and then when you're releasing from the magnet, gravity's helping you. It's pushing the object down, which means it's pushing it away from the magnet, and so therefore it's helping move it away from the magnet. And that's all he's not figuring, is that it's gravity. And it matters. Positions and angles matter to gravity, and so yes, the magnetic attraction isn't in free space. If you did the experiment in free space, you wouldn't have the same results. Free space, free from gravity. And so, a gravitational imbalance on the surface of the Earth. So it's just that imbalance that's breaking the apparent conservation, but there's no actual violation of conservation. You're just not accounting for gravity having a direction, and that the direction has the opposite impact in terms of releasing it from the magnet as it has in connecting it to the magnet. Alright, so that's a simple one. The more complex argument is this induction myth one, where he's doing the Professor Lewin experiment. Essentially, it's about Faraday cages and circuits, and I already did this video and computer froze. Froze without being, they're still recording the video, but I really couldn't tell, so everything was frozen, and it was frozen on the video. So I said, well, I could just pause it, but it didn't pause. Anyway, so I made the video, but it had a big giant gap in the middle of it where I'm just sitting here saying it's frozen, can't really do anything until it unfreezes. Me redoing that, it really isn't much point to me. So okay, just get to the point. Alright, so this is about Faraday cages. So the point is I already drew stuff. I don't know whether there's any value in it though, so maybe I won't bother keeping the old drawings, or maybe I will. So Faraday cages are traditionally drawn as bars, and you can have bars that are close together and bars that are far apart, and there's this idea that you put a radio inside of it and the radio can't receive any signal. Well, of course it does receive signal, and the simple way for you to understand how this Faraday cage ain't what people think it is, that it ain't some magical device, is that photons, light photons, are exactly the same kind of radiation as radio waves and all this other stuff. It's just the same stuff at a frequency. It just happens to be a different frequency. Theoretically, we could have an eye that could detect microwaves or some other radiation. It's just that through evolution, we're maximized to get the most out of our devices. And so we have a device that works optimally, and that's with visible light because there's more of it. The radiation, the sun makes a lot of visible photons, and so there's a lot of it, high density. And it has very good resolving power. You can see details really well. Too small a wavelength, and you start seeing through everything. Too wide a wavelength, and everything's kind of blobby and blurry. So light is kind of a really good range to be in, not to be seeing through everything, and not to have everything get blurry and fuzzy. So anyway, so obviously the point I'm making is that we can see right through the cage. So we know the cage isn't blocking electromagnetic radiation because we can see stuff going right through it. So we see the photons. The photons are electromagnetic radiation. We can see it. So no matter what you believe in wave theory, you believe in any ether, all that crap, it doesn't matter. You know that, oh, okay, it's the same energy. It's just a different frequency. So you can sort of understand that if the cage isn't blocking visible light, then it can't be blocking, radio or anything else in the sense of the obvious sense of blocking. It's blocking because the bars are close enough together to interfere with the ability to transmit the number of quanta of energy. The polarization breaks down essentially, and so it becomes a polarizing filter, and so it breaks the frequency coherency, and that's what makes it more effective against radio than light. But that's all it really is about. If you can make the bars really close together, you'd see, oh yeah, I can't see through it anymore. So if I make the bars close enough together, from a distance I won't see anything on the other side because of all the light diffraction. All right, so there's nothing magic about it. And then they mix it with this idea of somehow it blocks force with the idea that it's a conductor, and that's all it really is a conductor. And you can have a shielding conductor in the sense that if a lightning bolt hits you, it's not going to go to you because you're not ground. Right? If I'm inside of a round vessel and it gets hit by lightning, the lightning's going to say, where's ground? Where's the lower the potential? I want to go from high potential to low potential. I want to go from high pressure to the relief valve, the low pressure. I want to find the out, the exit. Well, the exit isn't inside the vessel, obviously. There's no ground in there. So obviously the closest ground is going to be the atmosphere outside the vessel, or if the vessel's sitting on the ground, quite obviously it's going to be the ground that it's sitting on. But the ground is going to be on the outside of the closed vessel. The closed vessel can't have a ground inside of it. And that's really functionally the way you need to understand it, is that you're not, there's no there's no reason for the electricity to go through some worse conductor to get to the point it wants to get to when it can just travel through the conductor. It'll do that instead, and it's always going to want to get to ground, so in a sense it's always going to want to make the atmosphere its way to get to ground, if that's the only way it can get there. So it just polarizes. So as a certain voltage comes in, it dissipates that voltage difference, in a sense trying to just find ground. And frankly, ground can be right here, or ground can be here, or ground could be anywhere on this surface. And so what it essentially does is just says, well, where's the place that is the closest ground? Now it'll tend, if you hit it with a lot of, if you hit it with a DC electricity, say 200,000 volts, it'll go, one side of it will go that positive voltage, and the other side will go negative, in the sense that it is going to try to transmit the voltage difference. So it's going to just say, this side, I want to create in the atmosphere the ions I need, and so I need to create a high potential in the opposite polarity to be able to travel through the atmosphere to get to the ground. And that's what it's going to try to do. So one side goes positive, one side goes negative. Now if it's a small amount of potential difference, it's not going to be able to do that. So it is basically going to just ionize the surface, and anywhere is where it's going to try to escape to ground. So it won't become one side's positive, one side's negative. And so the inside is just going to be a mixture of pluses and minuses, because you're really not going to bother changing the inside, especially when the vessel's big enough. One side isn't really going to communicate with the other side. Say, I have an electron over here, I have to have a proton over here. It's not going to be doing any of that crap. Basically, you're kind of not transmitting through the you've taken the signal. So again, this is done with an inductor that's an alternating current. So let's go back to the Professor Lewin experiment specifically. You can't really see that in this drawing anymore. So his experiment was, you have a circuit with two resistors in it. Alright, and then you put a inductor here. So you create an electromagnet, or you take a regular magnet and move it, but an electromagnet works because you can turn it on and off quickly, which is the same thing as moving it. And the point is that he's reading two different voltages from the same location, technically. And no, he's not, because what's happening is the radiation is going out to all of everything in Lewin's experiment. And it's also hitting the probe wires. So if I put two probe wires here, they're going to get hit with this radiation from the magnet. They're going to become inductors. So I'm really measuring a voltage out here somewhere on the probe wires. And so the probe wires are essentially part of the circuit. And that's what makes it possible for there to be these two different voltages in the same location, is because the length of probe wire affecting it in the field is going to be changed. And so the Tin Man's modification of the experiment is to put a toroid or whatever, one of these donut magnets, where the field is all in the inside because of the way the coil is wrapped around itself. So again, it's causing a bunch of internal reflections. And the clear point is that the only part that's getting radiated, there's very little radiation in the circuit here and here. So this coil doesn't radiate into the entire, it's not inducing current in the entire circuit. It's only inducing current in this one section of the wire. So it's essentially become a battery. And it's a battery you're switching the polarity of on and off, on and off, on and off. So the probe wires aren't affected because they're not in the field. So you don't have this probe wire problem. And clearly the only place that's creating that's getting radiated by the change in the field is the little piece of wire that's inside the donut. So you're making a donut magnet and you're putting the wire through it, and the only place that's getting affected is inside that inductor. And that's a simple answer. And so Tin Man guy's arguing something else, that somehow there is radiation when there's no source for the radiation. He can measure the radiation, so he knows it. Why is he arguing that it's there when it can't be there? And so he's arguing that because he put a Faraday cage around the little piece of wire inside the donut. So if I drew that, so here's your donut, and he has all the wires going through the donut. So I don't know how exactly to draw that so you'd understand it, but it's going through the donut. Yeah, well, that's how you draw it. Okay. So this wire goes over and this wire goes under. Okay. So it's going through the donut. So he says because he puts a cage around it, the wire, that therefore it can't induce, the magnetism can't get to the wire and induce the current. Well, of course it can. And whether you call the magnetism electric field or magnetic field, it doesn't matter. It's the same thing. It's all magnetism, essentially. It's all charge, essentially. And so you're going to, the cage doesn't stop the force. All it can do is collect it. But if it's alternating and you keep switching it on and off, well, then the field effect is going to be basically you're just going to turn the Faraday cage into a donut. It's just going to turn into the same kind of inductor because you're just going to keep switching the voltage, which is going to switch the potential inside the cage, which is going to make it an inductor too. And so it's not going to be effective in stopping potential differences. the change in potential. The change in potential is still going to happen because you keep switching one side positive and then switching it negative, then positive, then negative, then positive, then negative. And the same response is going to happen throughout the conductor. Whatever was positive is going to go negative, and whatever was negative is going to go positive. And so that's going to happen throughout the device. And so you're basically just going to create another field that's doing the same thing as the other field was doing, which is turning on and off, which is forcing the electrons to move, which is changing the pressure between the electrons, which is the very definition of a current. So, so the key thing to understand is there's no ground inside the conductor. There's no ground inside a garbage can. Okay, if I have a garbage can, Faraday cage, there's no ground inside of the can. So obviously, any potential difference, either too low or too high on the outside, isn't going to seek the center of the can because there's no ground there. So there's no door. The only place there can be a door is on the outside of a closed vessel. So that's why there's no current going through the center. There's no field going through the center, is because there's no point in going that way because it won't get you to ground. The flow wants to go to ground and finds the path that's the quickest and the least brambles, the least bushes in the way. I don't know how to say it. Finds the path that'll get it there the quickest with the most volume, and that's what it's going to do. It's going to go the quickest route. It's going to fall. I don't know. Analogies are dangerous, so I won't mess with any. It's good. It's just going to take the best route to ground, to the opposite potential. So if it's positive, it's going to seek the negative. And the hardest negative, the deepest negative, the best negative isn't going to be inside the closed thing. It's going to be somewhere on the outside. And that's where it's going to go. It's going to go back outside. All right. So, yeah, it's probably, I mean, you can say more stuff, but I guess that's what's, there's just all this mystique about Faraday cages as if they're magical. And like I said, you can break the magic just by understanding that light is electromagnetic. You don't see light affected by the cage, so you know that it's not something specific about cages, it's about conductors. And if I put a conductor around something, all the way around it, there's obviously not going to be a ground on the inside. And so obviously the high pressure or the low pressure isn't going to seek the inside, it's going to seek the outside, because that's where the low pressure is, or the high pressure that it's seeking is. That's where the difference is. The difference in potential. That's where the exit is. There's no exit on the inside. The exit is now on the outside. And that's all you really need to know. Alright, it's probably enough. I said more in the other video, so it was probably better in that sense, but maybe less is better. So, enough. So we'll see if he responds with anything. So I'm just pointing out. So he's saying he thinks, so you can see that in that little image. Can't really point to it. That the induction is somehow happening in the whole circuit, when clearly, because of the way he's focused the field, it's only going to affect that little piece of wire inside the field, where the field is strong. And that seems clear. And so obviously the Faraday cage he's made, the coaxial cable, fails to stop an inductor. It fails to stop magnet. Magnetism's hard to stop. It's hard to make a magnetic shield. It just isn't easy to do. And that's not going to do it. And it really is magnetism. I mean, when you're turning the inductor on and off, you're turning it into an opposite electromagnetic. South pole this way, North pole this way, South pole this way, North pole. You're switching the magnet back and forth. Same thing. That's what induction is. Induction is a magnetic phenomenon. All right. And obviously the other video, it's just gravity is creating the apparent difference. And it's only an apparent lack of conservation. There is no real lack of conservation. All right, so enough of that. We'll do some comments. Yay, it worked. See, this is where it stalled last time. I couldn't even switch pages and made a horrible mess. Okay, so this was a longer comment. Good for that's good, maybe. I have a question about light. I'm asking because number one, you seem to care about physics, and number two, your videos and answers seem based on logic, not beliefs. Well, I clearly believe things, so but yes, it's based on facts that maybe are solid facts. I mean, I don't have any, I don't believe in anything there's not factual reasons to believe. So yeah, I tend to go where the facts take me. And if somebody can tell me one of my facts is wrong, then fine, I'll change my facts. Demonstrate it though, don't just say it. Using our sun as an example, when light starts from a sphere, it goes in all directions. Well, see, the key is that it's not really going in all directions because the sun is a sphere. It's going in all directions because the atoms that are creating the photons, where the pressure is escaping, they are in a sense spherical, in the sense that they emit light in any direction. You know, a single photon will go this way, and then it can go that way the next time. The next time it'll go that way, and the next time that'll go that way. So when it releases energy, it tends to release it in all kinds of random directions. Or you could argue that each atom is shooting the photons in one direction, but it's randomized. So the next atom is shooting it this way, and the next atom is shooting it that way, and the next one's shooting it that way, and the next one's shooting it that way. So the point is that the energy is not being focused or lensed or in some way projected, controlled. So it's randomized in terms of the quanta when they leave the sun, leave in randomized directions. Okay, the light is seen as continuous with no gaps. But that's just how it seems, right? I mean, we know that that's not what happens. We know that essentially everything is time-lapse. Everything's a long exposure. So our brain is making long time exposures. It's not seeing the universe at the speed of photons. It's seeing the universe at the speed of like electrons maybe, or atoms, but it's not seeing it at the speed of photons. So it's not that kind of resolution. So in a sense, all of our perceptions of something are time exposures. You know, it allows more than one piece of quanta to come in before it makes a decision that a photon has arrived. So it's not seeing the quanta, it's seeing where the quanta are collecting. So yeah, so it's well, I think I've made the clarification. Light is seen as continuous with no gaps. There's lots of gaps. So after 1 second, the light has traveled about 186,000 miles in all directions, essentially forming a new sphere of light, yes, a new image, or whatever you want to call it, with a radius of 186,000 miles. After 1 year, the light has traveled 9 trillion miles, essentially forming a new sphere of light with a radius of 9 trillion miles, yes. Since the light is still seen as continuous with no gaps, the light is obviously expanding a lot. Well, as I pointed out, it's rays. So you can just understand that if I have a bunch of rays, you know, and they're starting from a sun this size, as they go out, the rays are diverging. They're separating from each other in two directions. So that's the inverse square law. The fact that they're moving away at the same rate in 2 dimensions. And so they're becoming sparser as you perceive them. And that's what a light bulb is doing. So, you know, and you could just say a laser beam has them focused, so a laser beam is breaking the inverse square law and sending a lot more photons a longer distance that you'll have as continuous because they're not diverging as much. But there's still a hell of a lot of divergence, as is pointed out, that if we shoot a laser beam to the moon, the spot on the moon is hundreds of meters wide. And it started off just small. All right. As continuous, no gaps, the light is obviously expanding a lot. The surface area of the 1 second sphere of light is way, way less than the surface area of 1 year surface of light. Well, obviously the number of photons are the same, and all the ability to talk, the inverse square law can also be understood as what happens when you take a sphere this big and you double its size. You quadruple its surface area, right? So you're just saying that the same light has to cover a much larger area. So if you're a grass cutter, for example, you could understand that it's a lot easier to cut the grass when the when the sun is this big than when the sphere you have to cut is this big, because now the grass is all separated, but you have to go across a lot of territory to get to each piece of grass. So yes, the grass is less dense. So the obvious answer, I could jump ahead and say that, well, the real answer to your dilemma is to understand that when we do see something from outer space, those are all time exposures. All right, we don't see a galaxy and say, you open your eyes, close your eyes, and you see it. You have to open the camera and leave it open for quite a long time for all the photons to finally get there, because they're just little tiny blades of grass, very sparse. And at each second, at each moment, you're getting this pixel and this pixel, and then the next moment you'll get this pixel and this blade of grass, and the next moment you'll get this blade of grass and this blade of grass. It just takes a long time before you get enough resolution to see the actual image, because you have to keep waiting for the randomizing of the image. You're getting this pixel, then you have to wait for a random change. You get this pixel, then on a random change, you get this pixel. That's the simple answer, I think. I think that's where we're going. All right. If the light is composed of photons or photon packets, it's quanta at a frequency, yes, in rays. So they're rays, lines. They're made up of bits, bullets. So they're bullets. You're shooting them from a gun, right? So what can happen when you're shooting the bullets from a gun? Okay, there's a certain amount of time, you're pressing the trigger, you're shooting the bullets. But the gun can move a little, and that's polarization. So because your gun moved just a little bit, even though you're aiming at the same exact place, you're hitting the target here, you hit the target here, you hit the target here, you hit the target here. So the bullets are a little bit out of alignment. That's polarization. But that's all there is here, okay? All the phenomenon that light creates can be understood as just understanding its bullets. There's a certain sequence, a timing event, creating the bullets. They're in rays. They tend to be in a ray, and the ray is a little bit sloppy. That's all you need to know. Those are the only important facts. Light is composed of photon packets or any kind of particle. The number of photons would have to multiply by a lot or expand in size by a lot as the sphere of light expands in size. So again, there's no expansion. That's why things get dimmer the further away they are. That's why the light bulb gets dimmer and dimmer and dimmer, is because the number of photons getting to you gets less and less and less, because they're getting further and further apart, and you're getting hit by fewer and fewer of them. But you have to remember that each wave of photons, each line of bullets, so there's guns shooting bullets, lots of guns shooting bullets, right, up and down. And at each moment, you're seeing a bullet from this guy, from this guy. The next moment, you're seeing a bullet from this guy and this guy. The next moment, this guy and this guy. All right. They claim to see light from millions of light years away, only billions, and that is an insane amount of light expansion. So again, I don't know what you keep thinking the light has to multiply, when obviously we have to leave the door open to see the tiny number of photons. Some of these time exposures are 15 minutes, half an hour. So you have to keep the thing focused on the same piece of space for a long time to get the little dribble that you're getting. And think about how bright the galaxy is if you were up close. I mean, all those burning suns, it's a ton of energy up close. Far away, it's a tiny amount of photons that you're going to get hit by. So what's hard to understand here? So why do you think that claim is insane? It's not an insane amount of light expansion. And that is hard for me to explain with waves or particles or both. Well, waves are silly. There's no medium. But clearly at a distance. So you can understand this. If I have just 10 guys and each guy is shooting bullets, you know, in a different direction a little bit, or they're randomized, and then you're 10 feet away, and you have a bucket, and you're going to collect the bullets. Well, you know you're going to collect more bullets 10 feet away than 1 mile away. The odds of one of the bullets falling in your bucket a mile away gets really thin. Okay, but the odds at 10 feet get pretty high that you're going to catch one bullet in, 2 minutes. Every 2 minutes you'll catch a bullet. But a mile away, it's going to take like every 3 years you're going to catch a bullet. Anyway. A wave would be so diluted from its origin. Well, a wave, obviously, yes, all waves spread. That spread is real energy going in real directions. Waves clearly are not perpetual energy in any of the mediums we watch them in. The wave function basically steals the energy. It absorbs it. It frictionizes it. It wipes it out. It sends it to a million different locations. So clearly photons aren't doing that. They don't get weaker. They just get fewer in number. As Feynman keeps pointing, as the father of quantum mechanics keeps pointing out, photons aren't waves. And yet people are clinging to it. And particles would have to breed faster than rabbits for the number to keep up. Again, they don't have to keep up. How do you not understand that when we look at a tiny little flickering star in the sky, clearly we're not seeing the number of photons we would see if we were a mile away from the galaxy. If we were a mile away from the galaxy, we'd be blinded by the brightness. I mean, clearly a light bulb from 100 yards, you can tell it's not nearly as hot. You can clearly understand the further away the sun is from us, the less, if I was on Saturn, you'd say, oh gee, it's not very hot today. Because the sun isn't hitting me with as many photons, not as many of those little bullets is getting to me. It's completely consistent with a particle theory. All right. There's no breeding of photons. The whole reason why the light is dimmer on Saturn is because they aren't breeding, and you're getting hit by a lot less. All right, assuming light doesn't gain energy along the way, how does the original light grow? So again, there's no evidence that it grows. There's every bit of evidence that the further away you go, the weaker and weaker the number of photons you get is. So much on a fixed amount of energy or momentum. Right, it was fixed as gigantic. Like on the surface of the sun, you're going to get hit by so many fucking photons. You'll be, evaporated by the number of photons. And here we're sitting on the Earth, and no, you don't get evaporated. You just get a little tan. Thanks for helping me understand. Oakley doke. Alright, so this Mike Summers guy just takes some rags at Ken. They seem pretty just stupid, useless. Looks like he hasn't dumped in a while. I mean, well, classy. He's no photographer. Well, he's not a very good photographer. He clearly understands the mechanics of the camera, though. His embarrassing snapshots are, yes, okay, yes, I don't know if they're embarrassing, but yes, he's not very good at saying, oh, that's a cool thing to take a picture of. Yes, his selection process isn't brilliant. Can one little photon jumps from pixel to pixel? That's not what he believes. He believes that somehow light is actually spreading, and that that there's a whole bunch of photons, or I don't know. Well, whatever he thinks. The whole wave is the ether jiggles because there's a whole bunch of photons spreading, but that doesn't make any sense, right? Because the single photon can't be a whole bunch of photons. So, yeah, it's stupid. Wave theory is just stupid. Ether is stupid. The whole thing is just stupid. It's just superfluous, and it breaks consistency. So it just doesn't work. It fails, as Feynman pointed out. Wave theory fails to account for the evidence. Okay. So this guy said, oh, this is a woke guy. So just a bunch more gibberish. Idiot. All right. So they have no channel. He's making a joke that in caveman talk, People can't like show up with an argument. You can't find one person somewhere willing to show how brilliant they are by proving me to be stupid, and yet you can't do it. You can't come up with a single volunteer. It's pathetic. Your weakness. Alright, so that's probably enough. So I had to do this twice, which is a little annoying. I didn't get to the comments section twice, so that was good. But anyway, but yeah, I didn't do the first part twice. But look, failures are part of the game. It's part of what you're signing up for. Failing, trying is signing up for failing. So anyway, till the next time, and such.